Complex numbers. So first of all, we're going to look at why we study complex numbers. Well, there's certain problems in maths that you will find that there are some real solutions and then no real solutions. So for example, if we look at the problem here. So if I want to solve this problem, I'm going to bring that plus 1 across to the far side. And what I get is x squared equals to minus 1. And as you remember from when we were looking at manipulation of algebra, if I want to find the square root, or if I want to find x by itself, I just square root both sides. But when I put in the square root of minus 1, so the square root of x squared just gives me x. But when I put in the square root of minus 1, I don't get an answer. I get a big error on my calculator. So that's a big problem. And as a way of resolving that problem or explaining that problem, we look at complex numbers. So one key thing to note about complex numbers is that we denote them using this I. And I represents an imaginary number. Okay? So I squared is equal to minus 1. So numbers of the form bi, where b is an element of r and I squared equals minus 1 are called imaginary numbers. So what you'll find is when we are studying imaginary complex numbers, we have two parts to the complex number. First of all, we have a, which is the real value. So that is your an element of the real number system. Real value. And then we have this b, which may also take on a real value, and that's attached to an I. Okay, so these are our real values, a and b, okay, but the I represents our imaginary number. So let's take an example. Let's say, for example, we had 5 plus the square root of minus 9. Okay, so if I want to write that as a complex number, the first thing what I'm going to do is I'm going to rewrite this square root. So all I'm going to do is I'm going to rewrite it as 5 plus. And what I want is I want to be able to I want to get back to this here, that I have a root minus 1. So if I think of factors of minus 9, I could have the square root of 9 multiplied by the square root of minus 1. Okay? And then if I look at the square root of 9, which I know is going to be, so 5 plus the square root of 9, which I know is going to be 3. But I actually have something to represent this square root minus 1 here, which is I is equal to root minus 1. So I can replace that with that I. So now my complex number is 5 plus 3i. This doesn't come up that often. Mainly what you'll be working with is this I squared is equal to minus 1. So a complex number then is any z, so we often see this in questions where it's related to or it's referred to as z, is any number of the form z is equal to a plus bi, where a and b are elements of r and I squared is equal to minus 1. So we said there in the last slide that a is called the real part of z, which is written as rez, and b is called the imaginary part of z, which is written as imz. C is just used to denote the set of complex numbers, so the fact that it's just outside the real number system here. When we look at complex numbers, they're written in this format, so this a plus bi. So the 6 is first, being the real number or the real part of the complex number, and then minus 2i is the second part, which is the imaginary part of the complex number. So the Argand diagram is just a visual representation of complex numbers, and it looks very like our xy axis that we use in coordinate geometry. Our real values are on the x-axis, and it's denoted by RE, remember that. And then our imaginary values are on the y-axis. And again, as normal, we have positive values here, negative values here, positive imaginary values here, and negative imaginary values here. So you can see here I have Z1. And what that Z1 represents is, well, let's look at where it lies. So we can see that here, in the real part, it's positive 2. so it's going to be 2. And it's also a positive imaginary number, so we can see that, or the imaginary part is also positive. So we can see that that's going to be 1i, or what we call I. If we look at plotting, let's just take another point. So let's say we want to plot the point, let's say we want to plot 5 minus 3i. Okay, so if we look over here, the real part is 5. So we have 5 here. So it's going to be somewhere in this part here because we have minus 3i. So on my imaginary axis, minus 3, 5. That means that our value is going to be plotted just there, or a little bit closer to there. Okay, so just a quick review then of the addition and subtraction of complex numbers. So when you have a complex number z1, which is equal to a plus bi, and z2, which is equal to c plus di, then all you do is you add the real parts, and then you also add the imaginary parts. Okay, so let's have a look at doing that here. Look at our first example here. We want to get z1 plus z2. So z1 plus z2 is equal to, we have 2 plus 3i, I'm going to put that in brackets, plus 4 minus 2i. Now all I'm going to do is I'm going to remove the brackets. So 2 plus 3i plus 4 minus 2i. And then it's very similar to algebra. So what we would have done in algebra, put our like terms together. So 2 plus 4 gives me 6. And then we have a 3i here minus 2i, which is going to give me a plus I. And that's my final answer. Okay, so let's have a look at subtracting this one here. So we have z1, which is 3 minus 6i. I'm going to put that in brackets. And then I have z2, so minus z2, and I'm going to put this in brackets, 2 minus 4i. And the reason I put them into brackets is because when I bring it down onto the next line, I want to remember to carry in that minus sign the whole way across. So what I get is minus 2, and then minus by minus 4i gives me plus 4i. And when I look at the like terms there, so I have 3 and then minus 2, and I have minus 6 plus 4i. My final answer there would be 3 minus 2 is 1, and then minus 6 plus 4i gives me minus 2i. So you may remember we covered something similar to this in coordinate geometry, which was called transformations. So what we just did there, adding or subtracting to complex numbers to move its position, that's called a translation, okay? And then dilation is multiplying complex numbers by a real number to stretch it. So for example, if we take z1 equals 2 plus 4i, and then let's say the question asks us for 2z1. All we would do there is multiply that 2 by 2 plus 4i. And very like algebra, just multiply that 2 straight into the bracket, so we get 4 plus 8i. And that movement there is called a dilation, so multiplying a complex number by a real number just in order to stretch it. The last type of transformation we're going to talk about is a rotation. And rotations are just when you multiply the complex number by I to rotate it 90 degrees about the origin. When we talk about it going through the origin, so for example, if we took this point here and we brought that out the exact same distance out the far side, that would be under reflection. So when we look at rotations, more so we focus on the rotations themselves. If we multiply it by I, we would be rotating the point Z1 anti-clockwise. So I'm going to show you that in a second. And if we multiply it by minus I, we're rotating 90 degrees clockwise. So let's first of all multiply this by I. So we have I by 2 plus I. That's going to give me 2i plus I squared. Now remember a little rule that said I squared is equal to minus 1. So I'm going to substitute that I squared now with minus 1. And what I'm going to get is 2i minus 1, because I'm just substituting that in for I squared. And remember, we just always write that with our imaginary number first, so that's minus 1 plus 2i. So if I go ahead and plot that now on my graph, minus 1, which is our real number here, plus 2i is going to be just about there. Which, if you look, is roughly, if I could draw a little bit better, it is 90 degrees about the origin. Okay, if we multiply it by minus I, so let's take it and say minus I multiplied by 2 plus I, and that's going to give me minus 2i minus I squared, because minus I by minus I gives me minus I squared. Replace that I squared with minus 1, so I get minus 2i minus 1, and that's going to give me plus 1, so that's going to give me 1 minus 2i, and I've just rearranged that there at the very end. So let's look where that would be plotted then. So we have 1 as the real number, and then minus 2i, so that would be somewhere down here. And again, you can see that 90-degree angle there. So the conjugate then, which often comes up, is the conjugate of z. So if z is a complex number a plus bi, then the conjugate of z is denoted as this z bar. And you'll see this sometimes. It could be w bar, it could be a bar, depending on what they've called the complex number. When you see that bar, you know that it means the conjugate. And all it is that you change the middle sign. So you can see here we have a plus bi, and now we have a minus bi. If you take an example where we have z is equal to 2 plus 2i, then z bar is equal to 2 minus 2i. Similarly, if we have a point that is z and it is minus 3 plus 2i, then our z bar is simply just minus 3 minus 2i. We do not change the sign in front of the real number. Okay, so one other thing you can be asked with complex numbers is what's called the modulus. The modulus of a complex number is just this distance from the origin. For a complex number a plus bi, we use the theorem of Pythagoras to find the distance x from the origin to a plus bi. So using Pythagoras theorem, we have x squared is equal to a squared plus b squared. We want to find out x by itself, so all we do is square root the other side, and that gives us the modulus. And just note that when you're looking at exam questions on this, it's denoted by these lines that we use for absolute value. Okay, so that tells us that what they're looking for is the modulus. Okay, so let me just quickly take you through an exam style question. So here we have the complex number z1 equals 2 plus I, where I squared is equal to minus 1 and is shown on the Argand diagram below. Find z2, which is 2 multiplied by z1. So if we take z2 equals 2 by z1, so that's 2 by 2 plus I, which is going to give me 4 plus 2i. And then the question there asks, find the value of z2, which we just have, and plot and label it on the Argand diagram. So we have 4 on the real axis and 2y on the imaginary axis. So that's going to leave it there, and just make sure to put in your label of z2. The second part of that question says z1 bar is the complex conjugate of z1. Write down the value of z1 bar and plot and label it on the Argand diagram below. So our z1 is up here, and that's 2 plus I. So our z1 bar is just simply 2 minus I. And if we're to plot that on the Argand diagram, I'm just going to plot it in red. So 2, positive 2, minus I, so on the imaginary it's going to be here. And that's our z1 bar. Okay, so the last part of that question then asked to investigate if the modulus of z2 is equal to the modulus of z1 plus the conjugate of z1. So first of all, what I would do is I'd find out what the modulus of z2 is. So the modulus of z2 then is just simply 4 squared, so that's the real value, plus the imaginary part, then the number there, the b value, which is 2 squared. And that's going to give me the square root of 16 plus 4, which gives me 20. Then I have z1 plus z1 bar, which is the conjugate. Now I'm going to go ahead and find out what the sum of those are first before I try and do the modulus. So I have 2 plus I, remember I always put them in brackets, plus 2 minus I. Remove the brackets, 2 plus I plus 2 minus I. We can immediately see there that we have a plus I and a minus I, so they cancel each other out. So my answer is going to be 4. Now, because we have no imaginary part here because they cancelled out, that's simply the modulus then of z1 plus z1 bar. Because we can't do the square root thing there because we don't have an imaginary part. And sure, we know then that 4 is not equal to the root of 20. So therefore z2, the modulus of z2 does not equal to the modulus of z1 plus z1 bar. The final part of complex numbers is just looking at the division of complex numbers. So, for example, if we have something like this, which we look at it and we can see it's kind of like a fraction. Very simply with these ones, like we would in algebra as well, is we just divide all parts of the numerator by the denominator. So we always want it to look like that a plus bi that we seen at the very beginning, z is equal to. So that format. So if I do that here, I get z is equal to 20 over 5 plus 10 over 5i, which we know can simplify down to 4 plus 2i. But let's have a look at something like this where we have an imaginary part below the line, so that's a complex number below the line. What do we do then? Well, step 1, we get the conjugate of the denominator. So this denominator here, we have 4 plus 6i, and we want to get the conjugate of that, okay? And that's going to be 4. Remember, all you do is change the sign in the middle, 4 minus 6i. Step 2 then is multiply above and below the line by the conjugate. So all I'm going to do is I'm going to put in here 2 brackets, and on this side I'm going to put in 4 minus 6i all over 4 minus 6i. And for your convenience, what I'm going to do is I always start in the bottom first and multiply out the bottom and then multiply out the top. So if I look at multiplying below the line first, say 4 plus 6i multiplied by 4 minus 6i. You can use the split the bracket method here from algebra. You know, I'll go ahead and use that myself just as a little bit of revision. So 4 multiplied by 4 minus 6i plus 6i, so taking the second part of that first bracket, multiplied by 4 minus 6i. Do my loops then, so 4 by 4 is 16, 4 by minus 6 gives me minus 24i, positive 6 by 4 gives me plus 24i, and then I have minus 6i by plus 6i gives me minus 36i squared. Okay, we can see immediately that these two cancel off. And what I get is, I'll change the black here just to make it a little bit easier to see. 16 minus 36. And remember that I squared can be replaced by minus 1. And that's going to give me 16 plus 36. Which then is going to give me 16 plus 36. That's going to give me 52. Let's look at above the line then. So if we move back up here, we can see above the line is 11 plus 10i multiplied by 4 minus 6i. So 11 plus 10i multiplied by 4 minus 6i. So if I multiply them, I'm not going to use split the bracket this time. I'm just going to go ahead and jump in and multiply them. 11 by 4 gives me 44. 11 by minus 6i gives me minus 66i. 10i by 4 gives me plus 40i. And then I have 10i multiplied by minus 6i gives me minus 60i squared. That'll give me, so I have 44 minus 66i plus 40i is going to give me minus 26i. And then I have that minus 60, but instead of I squared, I'm going to put minus 1. I'm going to simplify that. I'm going to get 44 plus 60, which is going to give me 104 minus 26i. The last part then in all of this, all I'm going to do is I'm going to take all of those two answers there and I'm going to put them on the top and bottom. Okay, because this one here, the last one I've just highlighted there, represents above the line, so that's 104 minus 26i, and the other one represents below the line, which is 52. I'm going to write that, make sure to write that in the form of z equals a plus bi. So if I look at 52 goes into 104 twice, so in this case my z equals to 2 minus, so 26 over 52, that's going to give me half I. Okay, all I simply did there is I just rewrote this as 104 over 52 minus 26 over 52i, and then simplified it to get this final answer.